State University and was on the faculty of Kansas State University before switching his allegiance from purple to crimson and blue, 1978.
Yeah. So today we'll look at the High Plains Aquifer, look at both net inflow and specific yield variations across the aquifer. I'd like to acknowledge the Kansas Water Plan and the USDA for support on this particular project, as well as in the past, NSF funding. The team here we have in the Geohydrology section that has worked on this up to this particular date, but you saw a couple or new individuals will probably be joining in later. So we've got Jim, you saw a lot this morning, and Brownie's not here. Jeff Bowling and then Kai Shung, who is over here. So this particular team has worked on the High Plains Aquifer for a number of years. For today, the takeaways give you at the very beginning is that what we have found is that the net inflow in the High Plains Aquifer is actually greater than people thought in the past. So that means that if you look at the pumping reduction to achieve sustainability, it's actually not as great as people thought was needed in the past. So this means that the farmers can actually have a more practical reduction in terms of their farming practices and really do a good job on reducing groundwater level decline. The other is that the specific yield that we have found from methods we've been using is actually a lot lower than people have used in the past. And this has very important ramifications on the numerical models, numerical groundwater models. Those models then have been predicting also too high the pumping reduction needed for sustainability. So these are very important findings that we're making. And here I'll show you some of the variations in the net inflow and the specific yield, which are then also very important in terms of maybe how you might want to do modeling in the future, because then you could maybe tailor-make some of these values for particular zones in the aquifer. So we have the 5 groundwater management districts, and you can see, of course, the western part, it's a lot drier, and I guess, as has been mentioned before by Dave Barfield, that it's wetter out in this particular area. Now, Kansas is blessed with great data. We have about 1,400 wells that are measured each winter by the Division of Water Resources and the Kansas Geological Survey across the High Plains Aquifer. And then we have the best water use data in the nation, because we have the greatest number of wells that have been metered with now totalizing flow meters. And you can see we've got a tremendous number of those, and the Division of Water Resources does an excellent job in then quality checking this data, as well as the groundwater management districts that are going out there and making sure that people are abiding by the correct procedures and the correct equipment to measure the water use. So today I'll talk about 2 particular areas, groundwater management district number 4 and groundwater management district number 5. So we've got the western area here of the Ogallala, and then we've got the south central area of the Quaternary aquifer. So the Kansas Geological Survey was examining the correlations between the water level changes and the water use, as well as climatic indices, and we're finding excellent correlations, highly statistically significant. And then Jim went and looked at this, and he put the theory to this, and then was able to come up with the appropriate equation for the water balance. And this is presented in this particular slide, so that we've got the water volume change in the aquifer equaling the inflows minus the outflows, which then can be rewritten to separate out the pumping so that we have net inflow minus pumping. Then, if we look at the water volume change, that's the water level change times the area times the specific yield. And then if we say that the net inflow is I and the Q is pumping, then we can rewrite the equation in terms of the change in the water level, and that particular way in which Jim rewrote it is a linear equation. So then we can look at the change in the water level versus the water use, and we do this on an annual basis, and then we plot those, as I mentioned, and then we can determine the pumping when the water level change is 0, and that's the Q stable, or the pumping for sustainability. So we can have that as a volume, we can have the inflow at that particular Q stable, or if we want to think of it, for example, like the idea of the recharge, you usually think of maybe so many inches or so per year. So we can have that as a depth, simply divided by the area. And the theoretical portion of this is published in the paper here in Geophysical Research Letters. So if we plot some of these data, we can see here average annual water level change versus the annual water use. And this is for groundwater management district number 4 and 5. You can see here's the linear regression in each case, very highly statistically significant. And then if we go here to the 0 water level change, come over to the linear regression, come down here, we can see the actual then volume per year. And then we can see what the average pumping is. And the difference between those is the amount that you'd have to reduce pumping to gain this sustainable condition. And for GMD4, it's 21% for these data for 2005 to 2017. For GMD5, it's only about 1.5%. Now, we can also correct this for climate by utilizing the correlation with the climatic indices. In that particular case, this would be 24%, and then this would be about 6%. So it's been somewhat wetter period in the particular data period that we're doing this for. Now, a couple of assumptions we have to have here is that those water levels, those average water levels, will be representative of the particular area. And Jim and Jeff Bowling have been working on that and found, yes, that looks like that indeed is true, and also that the net inflow needs to be relatively constant. I know that's, Jim has been looking at that too, and it looks like that is a pretty good assumption. So let's look at some values here. For the whole of the GMD, we see for GMD4, somewhat over an inch, for GMD5, about 2.4 inch, but that's for the total area. Now, if you actually look at the GMDs, you'll find there'll be some areas where there aren't pumping wells. So what we did then was to look at, say, a buffer around the wells. For example, a 2-mile buffer, a 1-mile buffer. In that case, most of those circles overlap and cover nearly all of the areas of the major pumping areas. But if you do it with a 1-mile buffer, then you see that these values will increase because in that particular case, the area will be smaller. And so we have about 1.7 for GMD4 and about 3 inches for GMD5. Now for the Ogallala area, those values, 1.7, is a lot greater than the values that have been typically assumed. So we find that, again, that's very important because that shows us that the reduction in pumping needed is not nearly as great as people thought that was coming out of some of the numerical models. So therefore, the farmers, in a practical sense, can actually achieve some of those pumping reductions and do a great deal to slow down the declines. In GMD5, the value is closer to, say, a combination of precipitation and irrigation return flow. It's not as much water level change there. So now, in terms of looking at some of the variability on the smaller scale here is for the counties. So here are the net inflows based on a 1 mile buffer for the county areas within GMD4. When I say significant here at a P, this is for that relationship of the change in the water level versus the water use. One of these counties didn't do as well. The rest of them less than 0.01 P. This particular county, Cheyenne, there's more uncertainty. But you see the values range from about 1.1, about 1 up to 2. Now if we look at the Sheridan 6, and Dave Barfield gave you a presentation on this, so I don't need to go through that. The Lima, Local Enhanced Management Area. So you see that inflow is greater. So in that particular area, we have more permeable sediments, and we have a greater pumping density. And so when we look at some of those here, say with the county areas, we do indeed find that the higher values are generally associated with the greater pumping densities. And therefore we have greater irrigation return flow, we have greater drainage of the newly unsaturated zone that's been created. We may have some greater lateral groundwater discharge because of some of the changes in the groundwater levels. So all of this, we believe, is making sense. And again, even greater values here because this is a more permeable area, greater pumping density. So now we move to groundwater management district number 5 to see some variability. And you can see that these range from somewhat over 1 up to 4.2. Again, this is net inflow. So don't think of that as being just the recharge. It's all of the different factors that would go into the inflows and the outflows without the pumping aspects of the net inflow. So you can see some variability, and we can see the higher values over here in the west. Generally, we've got some good pumping densities as well as some greater depths to water in that particular case, some more water level declines. So that all goes into what produces those greater net inflows. So then we did this on the smallest scale, individual index wells. And so I'll show a couple here. See, we get very significant relationships with the change in the water level, with the water use. Now, one problem here is that assumption that that water level is going to be representative of the area is not quite as good here. So we do see, when we look at some of the changes based on using different areas, there's a lot more variability. But still, it gives us some idea of the net inflow in these instances. So in that particular case, for this Thomas County well, we've got in GMD4 3.5 inches per year and 3.3 for a well at Belper down in the western part of GMD5. And that's for a 2 mile radius area, which was for how I express these particular graphs. If you do it for a 1 mile radius, you see then it's even greater. So conclusions for the net inflow part of the presentation. You see this water balance approach can be used very nicely for getting at estimating net inflow. And so we can look at a wide range of scales, about 1.7 overall for GMD4 and about 3 for GMD5 based on 2005-2017 data. Then inflows are about 1 to 2 inches for GMD4 and about 1 to 4 inches for GMD5. And if we go down to the index well, somewhere in the 3 to 4 inch range. And again, these are substantially greater than previously thought for the different areas, especially the Ogallala region. Again, that has ramifications on practical reductions in pumping to achieve slowing down water level declines. So we come back to the same equation, and then we can look at this in terms of, again, you plot the water level change versus the pumping, and then the specific yield is 1 over the slope of that line times the area. So again, take the slope, went over the slope, and then include the area, and we can get out the specific yield. So if we do that, you get 4, GMD4 for the total area, value a little less than 0.06, for GMD5, a value a little over 0.02. And if we look at the 2 mile to 1 mile buffer areas around the wells, then that gives us some values here about 0.06 to 0.08 for GMD4, 0.025 to 0.029 for GMD5. Now, again, we look at these values, they are a lot less than what has been used in some of the models. For example, the Republican River model used a value, I think was 0.175. And then if we look at the GMD5 area, that is 0.2. So that's almost a factor of 7 times difference. So now if we look at the specific yield for the counties, you see the range in the values here, values that might be down as low as about 0.03, and then going over a little over 0.1. Again, this particular one, we have the lower P, maybe not really statistically significant, so that has more uncertainty. But you can see the range in the values, and in general, the higher values are, again, in some of those areas where we have the more permeable sediments. And so this, in general, fits a map that Jeff Bowling has produced based on lithology, based on an analysis of lithologic logs for groundwater management district number 4. So for the Lima, Sheridan 6 Lima, you see 0.12, again, being an area of intense pumping and generally greater permeability of the sediments. We look at, oops, that should be 5. Okay, if we look at GMD5, then we see a particular range in these, and the higher value are down in this particular area. But you can see there's some range in the values as well. But still, again, a lot lower than the 0.2 that's been used across. So, again, if we're seeing some of the range in these values, we might think in numerical models actually of some kind of zonation in specific yield. And indeed, Gaisheng Liu is working on this and different approaches for doing modeling with these lower specific yields. So I show this again, simply to remind you, you can also do this down on the small scale for the individual index wells. And if we look at the specific yield there for a 1 mile radius for the Thomas County well and then the Belpre well, but then you can see there's a lot of variation here if we go to the 2 mile radius. So that's where maybe we're getting in an instance where maybe that water level isn't quite as representative of that whole area because it's just that one well. So the specific yields are substantially lower than, again, that have been used in the past. So why? Well, the flow models generally come up with a tabulated value for homogeneous units in lithologic logs or pumping test values. And so they're not really representative of the regional values. The actual aquifer sediments are highly heterogeneous. There are a lot of low permeability layers, and those may exert a substantial control on the drainage in the system. Also, what are the lithologic logs for? They're for completed wells. They don't include all of these test wells that are out there, which will probably have lower permeability, less permeable sediments, because they're going to put in the irrigation well, they're going to choose the sweet spot. And maybe the drillers don't fully capture the fine fraction of the sediments. And also, if you entrap air in the water level change zone, you'll find that will decrease the specific yield because you've got some air in filling some of those pores. So the implications of using too high a specific yield in the numerical models, average net inflow would be too low. Inflow for the dry or wet years goes up and down a lot more than one would expect. And percent reduction in the pumping to achieve the stable water levels will be too high because the average net inflow will be too low. So conclusion for the specific yield, again, we can use that water balance method for getting at the specific yield using that annual water level change versus water use regression. And we could go at a range of different scales. These values are somewhere in the 0.06 to 0.08 range for GMD4 and somewhere about the 0.025 to say 0.03 for GMD5. Again, based on this set of data that we have, and then using 2 mile to 1 mile buffers around the wells as a better representation of the area. And then we can go look at some of the variability for a smaller scale and get a bigger range in the different areas from the counties to the Lima to the index wells. And finally, again, just to emphasize that the SY values, the specific yield, are much lower than those that have been used in prior regional models, including the ones that we have had in the past. And now, Kai-Sheng Liu has been working on looking at the lower values and the deeper. He's gone back to the GMD1 model and found that by utilizing those lower values, he now ends up with pumping reduction values that fit more in the line with a water balance approach. And Jim talked about the refrigerator magnet, so you can go online and see our High Plains Atlas. I don't know, you still have refrigerator magnets to hand out? Or you didn't bring them?
I've got 3.
You've got, oh. And then if you want to look at references here, references, including a new one we hope to come out pretty soon. Jim is working on the final revisions for response to the reviewers that will talk more about this issue of the specific yield. Questions?
Don, you're using the aerially averaged change in water levels to get at these kind of net inflow estimates. And I was wondering if there might be hope to use the spatial distribution of the actual water levels to separate out that net inflow into a lateral and a vertical component based on the kind of spatial distribution of the hydraulic gradient.
Interesting question. Mike, what is your response to it?
Yeah, I'm not sure our quality of the data is good enough to get gradient measurements. So that would be a challenge, but sure, we could work with that.
Anyone else?